Right, great. So I came across this paper because it is related to my own research on how to evaluate the interventions in infectious disease settings where you intervene on an individual, but you does not like you don't only affect the outcome of that individual, but his or her contacts. So indicated in this title, the authors argue that traditional regression models cannot be used to identify risk factors from observational studies in the infectious disease settings. So let me give a brief overview of the introduction, methods, and results, and then we will discuss the questions. So a bit of background. In epidemiology, regression models are commonly used to identify risk factors by comparing disease risks in different groups. And multiple studies applied regression models with ethnicity as the exposure and SARS-CoV-2 death as the outcome. Sometimes they also considered like SARS-CoV-2 hospitalization, and etc. They are cited in this paper by the authors. Like they give like at least 10 or maybe 5 to 10 examples. And they use, in those studies, they use observational data while adjusting for covariates to show the association between the ethnicity and also the transmission disease outcome. The association is often expressed in terms of hazard ratio or relative risk. The authors argue that the regression models are not suitable for identifying risk factors for infectious diseases. This is related to question one that we will discuss in a moment. That is, do you agree with that argument and under what circumstances, if so? By the way, I forgot to mention, yeah, please jump in or type in the chat any question you have anytime. So the goal of that the author wants to achieve is to investigate the consequences of applying the regression models to analyze individual level risk of infection. They simulated different SIR models, structured SIR models with two populations and applied the statistical methods such as Poisson regression to the simulated data. And they show that they will get a different result than what is expected if they apply the Poisson regression to study a non-communicable diseases. So I would like to define a few key terms related to their methods and results. So in the example settings of two ethnicity groups, associative mixing means that individuals mix more contact within a group than between groups. So associativeness or associativity of X is defined by the relative number of contacts within to between the groups. So an associativity of X means that individual makes X times as many contacts within those of their same group than with individuals of the other ethnicity group. In this paper, the author varied this parameter X in different scenarios to show that regression models are not suitable for identifying individual level risk factors when there is associative mixing. Another type of mixing they mentioned is called random mixing, which means that every individual has the same probability of being in contact with another individual irrespective of the ethnicity group, which is not always the case in reality. Okay, let me briefly summarize the approach they use before getting into the results. So sorry about the wordy slide, but this is that from next slide on, there will be graphs. So to illustrate their points, the authors consider 4 scenarios. In cases 1 and 2, they structured an SIR model with 2 populations, and in 3 and 4, they structured a model with 4 subgroups. They simulated the epidemics using the models and applied the following traditional statistical methods to the simulation outputs. So in case 1, they computed the relative risk. In case 2, they fitted a Poisson models with 1 independent variable to show that the fitted Poisson model cannot predict the true proportion infected. And in cases 3 and 4, they fit a Poisson model with 2 independent variables. One independent variable is adjusted in order to identify the effects of ethnicity on like infection risk. They do that to show the magnitude of the regression coefficient is subject to associative mixing. So here are the estimates of interest in different cases. I think case 2 is a little bit hard to understand because they are trying to predict the proportion infected. Okay. So I'll go over the methods and the results of each case. So the setup of case 1 is that there are two risk groups. B has a higher susceptibility compared to A. That is, compared to a susceptible individual in group A, a susceptibility individual in group B has 1.2 times the probability of infection upon contact with an infected individual. Here in case 1, there is no contact between the two groups, so you can basically consider that they are two separate epidemics. The estimate of interest is the relative risk, or actually it is the cumulative incident risk of infection comparing group B to group A, the high risk to low risk group. The result is shown in figure 1 here. Their conclusion is that relative risk is highly dependent upon the point at which the relative risk is computed, such that the RR, the relative risk at a single time point, cannot be interpreted as the effect estimate for that individual's the exposure of that individual, the individual level risk factors. So figure 1 is related to our second question, that is, what can the temporal change in RR tell us? Is it possible to know which stage of epidemic, that is the beginning or the end of the epidemic we are at, by looking at the RR at different time points? So let's go to case 2. So in case 2, there are two risk groups, with B having a higher and a varied susceptibility than A. That is, B has a higher susceptibility than A, and then they repeatedly simulate a series of scenarios, and in each scenario, they vary the susceptibility. So this time, there is random mixing between the two groups. That means like people come into contact with one another irrespective of their ethnicity group. So the approach in case 2A is that the authors simulate the epidemic under a series of scenarios for which they varied the susceptibility of group B. They trained the Poisson regression models that is given in this formula here in the presence of both group A and B. Then they use the trained model to predict the proportion infected in the absence of group B, that is, when the whole population only comprised of group A individuals. It may sound a little bit weird why they take out group B to predict the risk of group A. So their idea is that if the trained Poisson model is correctly specified the model, then the predicted proportion in group A, that is the low risk group, should be the same for all scenarios, irrespective of the susceptible parameters, or irrespective of the susceptibility of group B, because there is no group B in this new population that they try to use the old model to predict the risk for. Any questions? I think. Okay. Let's look at the results. So as shown in the figure 2A, this panel on the left, this Poisson model is a misspecified model, because across the 4 scenarios they consider here, the predicted proportion infected now in a completely low risk population turns out to vary, and the proportion turns out to increase when there's no high risk group at all, and it increased with the susceptibilities in the original population where there were high risk individuals. So to put it in the other way is that the proportion infected in the low risk group varied depending on the susceptibility of the high risk group at which the Poisson model was originally trained for, even though it shouldn't, because there is no high risk group in this new population. So you can see by the orange dot, that's the true value, that is the true proportion, sorry, not proportion, I've been saying about proportion, but the true total cases, like group, the 2B is for proportion, but 2A is the total cases, but you can just divide it by 100,000 to get the proportion. So so the true friction infected is the true number of cases infected under the simulation is invariant, regardless of what the susceptibilities of group B is, because there is no group B. Okay. So case 2 B plots the proportion infected in the low-risk group in the original simulation when there were two groups. This shows that the infection risk of group A depends on the susceptibility in group B. So the higher the susceptibility of group B, the higher proportion of group A individuals will be infected. Any questions? So the conclusion is that figure 2 showed the interdependence between high and low groups. That is the fraction infected or the total cases in the low risk group depends on the susceptibilities of the high risk group. And then the Poisson regression cannot disentangle the effects of interdependence from the effect of individual risk factors. Let's go to case 3. So the setting is that there are two ethnicity groups, each with two risk level. So group B has 50% individual with higher risk, while group A has 10% individual with higher risk. That is, B has a high proportion of susceptible individuals than A. In case 3, there is associative mixing. The number of contacts within their own group is 8 times the number of contacts between the groups. Their approach is to simulate the cumulative number of cases in all 4 groups, fit a Poisson regression model that is given in the formula here to the cumulative number of cases, and consider the coefficient for ethnicity to study the association between ethnicities and infection after controlling for individuals' risk group status. Their idea is that if one analyzed the data as if their outcome were an NCD, a non-communicable disease, let's say diabetes, then ethnicity should have no association with the diabetes outcome after adjusting for the individual risk group status. The result is shown in figure 3b here, that even though one may expect no association between the ethnicities and outcome if it were an NCD, we still see that the exponentiated coefficient deviate from 1 as we increase the number, like the degree of associative mixing. Specifically, this estimated coefficient depends on the associative mixing because it is an effect of associative mixing. So the conclusion is that the observed effect is due to positive associative mixing within the ethnicity groups. Finally, let's quickly go over case 4. Case 4 has the same setup as case 3, except that the high-risk group is characterized by more contacts, like a higher making more contacts, like each individual make more contacts, rather than having increased susceptibility compared to a low-risk group. The result is showing in figure 3c here, which makes the same point as figure 3b in case 3. That is, the Poisson model cannot capture associative mixing, which affects the effect estimate, so the estimate should not be interpreted in the same way as in NCD. Okay. So I think I kind of finished early, but yeah, here are some questions that I'm interested in hearing more about your thoughts on.